Hello there, this is Toby, and we're going to continue the series where we follow the LLVM tutorial to make a toy programming language called Kaleidoscope. So yeah, we're at chapter 2. Last episode and last chapter, chapter 1, we made a lecture which is able to give us a series of tokens. So if I type in a number like 23.45, it'll recognize it as a number, and I know it recognizes it as a number because -5 is the code for a number token, number. And if I type in something that looks like a variable name, let's call, I don't know, foobar. Foobar definitely looks like a variable name, and it recognized it as code -4, and I know that -4 is the token type for identifiers, right? And there's also a token type for the def keyword and the extern keyword as well. So def and extern yield their respective token type numbers. So I can verify that the lecture works. Again, all of the code is supplied by the tutorial, so although there might be places where I decide to go off on my own a little bit if I'm feeling brave, but for the most part I'm going to be following the code in the tutorial. And at various points in the tutorial they actually give you the full listing of the code, like at the end of chapter 2, this section, they'll give you the full source code. So in case you made a mistake somewhere along the way that you couldn't figure out how to solve, you can always just copy their code and have a working copy of the code. Okay, so in chapter 2, that's what we're doing. I might split this up into 2 parts. I'm not sure yet because chapter 2 is kind of a long, lengthy section of this tutorial. We're going to be making a recursive descent parser complete with operator precedence parsing. And this is actually something that's very interesting to me personally because I've been recently spending some time learning these things. How to hand code a recursive descent parser in particular without using the help of a parser generator tool like Nearly.js. In the past, I have created some material, some online material teaching people how to use a parser generator called Nearly.js to help you build a parser in a very quick way. But it's also worth, if you're serious about compilers, learning how to make compilers, you should also learn how to do it the hard way as well. And the hard way is writing a parser by hand using the recursive descent technique, which is what we're going to do here. First, let's start with the abstract syntax tree. Okay, we're going to make a class hierarchy or a bunch of classes representing the different AST nodes in this programming language. Each AST node type they'll be represented by a specific class with a thus named name that represents that type of syntax element in the language. And if we go back one chapter, let's just go back. So in chapter 1, we saw a very small example of a program in this programming language. It's called Kaleidoscope. So the programming code in this programming language looks like this. It's got a def keyword. It's got identifiers, like any normal programming language. It's got identifiers. It's got operators, like less than signs, minus signs, plus signs, etc. It's got comments. Each of these types of things is like a syntax element in the language, and they need some representation in the AST. Like the def keyword needs an AST type that represents the def keyword, and a identifier or a variable or a function definition such as this one, or variable reference or if statement. All of these things need a syntax element that represents that thing, or a class that represents that syntax element. And that's what we're gonna be making. So we're gonna make one base class called the expr AST, and then all the other classes are gonna extend from that to be their specialized type of AST node. Okay. Okay, we're continuing on. Just gonna keep working in this file. I'm gonna comment out this main function, which I wrote just to test out the lexer. The tutorial didn't instruct me to do that. I just decided to do that on my own. Okay, so I'm gonna type in this code. Okay, so this is the base class from which all of the specific AST node types will extend. Oh, by the way, you have to put a semicolon after each class definition. What is defined here? Well, we defined this destructor, which is virtual. That actually kind of confounds me a little bit. Why we define this as virtual, but I have a feeling is because if we didn't define this, then C++ would want us to define it. So this is just going to preemptively define it. And the fact that it's virtual means a subclass may choose to override its implementation. I think that's what it means. Yeah, I'm not exactly a C++ expert, but that's my guess as to why we need this. Okay, now that we have the base class, we're going to make a number expr AST to represent any numbers in the program. This colon means extension, so number expr AST extends expr AST. Why do we need to write public here? Turns out that in C++ there's a concept of sort of making it public, the fact that you inherit from another class, versus keeping it private. I haven't seen that concept in other languages, so I believe this is unique to C++. If you do not make it public that you extend another class, I believe then the consequence is you're not allowed to cast a object of this class to a variable that has the type of your parent class. You are only allowed to make that cast if you made it public that you extend that parent class. I hope I'm right about that. And instead of giving out false information, again, take what I say with a grain of salt, because I'm not a C++ expert, although I am trying to be. Okay, what is this guy? Well, this is the constructor. A constructor has the same name as the class, and it looks like a method. And then what is this thing after the colon? That is called the initializer list. All this does is really assign this value to this variable inside the class. So if you're a Java programmer or even a JavaScript programmer, you're probably more used to doing this. Like you would do like this dot val equals val, like that. Well, this initializer list thing just does the same thing with a different syntax, and you can do it either style. And also this name here, it's slightly confusing that it's val val. So they are referring to two different things. Like this one is referring to this one, whereas this one is referring to this one. So you could actually call them different things. So I'm gonna call this one, let's say I call this one V, right? Let's do capital V. And this does exactly the same thing, right? Yeah, so I'll leave this one like that. It does the exact same thing. Okay, so I'm gonna define the other ones. The other ones are gonna be pretty much the same style, just with different types for their variables. I'm gonna copy this one to be a little more expedient here. One thing I want to say is when you're dealing with a string, I actually don't 100% understand why we need to define the input parameter of this constructor to be a const string with an and. The and, I know what the and means usually. The and means the address of. So if you have a variable in C++ and that variable is like a string, well, the string is stored in memory somewhere. And that memory has an address location, which is usually a hex number like that. So if you put an and in front of that string variable, that gives you the address location where your thing is stored as a number. I don't actually understand why this is used in the context of a parameter list. I'll have to read more about it, or if somebody knows, if you're watching this and you know the answer, please enlighten me. We have a binary expr AST. I'm gonna type this out because there's some stuff about it that I would like to slow down and talk about. It also extends the base class expr AST, and it has a char. It has operator, which is a char. So the operator is like a plus, a plus, minus, multiply, divide, or greater than, less than, etc. One of those operators. And then we have a unique pointer. And that I might need to explain a little bit. I actually was completely clueless to what it was earlier today until I researched it a little bit. But let me type this out first and then I'll explain. Again, we're going to use this pattern of just passing in these parameters into the constructor and then just using the initializer list to initialize these three variables. And each one of them is actually a unique pointer to a expr AST. And then we'll do this initializer listing. Okay. I think that's it for the binary expr AST. Wait. Oh, I have an extra comma. Was that the problem? The extra comma? Op is a non-static data member. What's the problem? I need a semicolon? Oh, op, it needs to be capital OP. Okay, that was it for op. But what about left hand side and right hand side? It's a deleted function. cannot be referenced. Oh, I need to do this standard move thing. Okay, I see now. Well, I don't know if I can explain this one, honestly. Does that work? That works. Okay, good. I didn't even copy this code correctly because I wasn't going by. Okay. What is this unique pointer thing? Unique pointer in C++ is what they call a smart pointer. Okay, a smart pointer. And I guess it's a relatively new innovation in C++. I guess if in order to understand why a smart pointer is needed, you have to understand more about, well, what did people do before there were smart pointers? Well, they just had pointers. they didn't have smart pointers at one point, and they just had pointers. What the heck are pointers? So whenever you have an array of stuff, a type that has a combination of stuff in it, so an array or an object or a dictionary or any of these things, when you have a variable that is the array, like I have an array, it's actually a pointer to some location in memory that contains the actual data. Well, okay, that's in C++, that's not totally true. Sometimes the data is right there on the stack for you, but in many cases you're dealing with a pointer. And a pointer is sort of represented as an address location, right? If you know where this stuff is stored in your memory, you know the address of the stuff, you can go there and get it. Therefore, a pointer is in reality a address location. Now, somebody has to be responsible for cleaning up this memory location, as in, if you're gonna claim a section of memory, well, that's like that's kind of a big deal, because if you weren't using that memory, somebody else could be using it. So there's this concept of ownership of memory. So if you're gonna use your memory and you're done with it, you better free it up so that other people or other parts of the code can use that memory. And in some languages, starting with Java and JavaScript also, and Python and Ruby, most of languages have this thing called the garbage collector, so that you don't have to, so that the developer doesn't actually have to explicitly say, free up this memory, I'm not using it anymore, so other parts of the code can use it. But C++ doesn't have a garbage collector, and C and C++ and Objective-C as well, they do not have a garbage collector, and the programmer is actually responsible for freeing up the memory that they use when they're done with it. Which means, and in the past, the way C++ dealt with that is to say, well, when you're making a class and this class is not needed anymore, or an object of this class is not needed anymore, it goes out of scope. Say you have a variable. Let me make an example actually. Let's say you have a function, some fun, and then you make a variable of some sort of class. I'll call this benExpr, like that, and it's initialized with some value, blah blah blah. You do some stuff with it, but because this variable is declared within the body of this function, when this function is done, we actually don't need this variable anymore, and therefore any memory that this variable uses can be freed up implicitly. When you make a class, though, you might do something in the constructor or in its method that claims additional memory. And if you do that, then it's your responsibility to clean it up. In the destructor, what's the destructor? Well, it's written like this. It also has the name of the class, but it has the tilde in front of it. So if you allocate for some memory here, let's say you do like some other thing I need equals new that other thing. This new statement allocates memory for that other thing. And because this is C++, and you want to be responsible, you're going to need to say delete that some other thing that I need within the destructor to properly clean up after yourself. Smart pointers, coming back to this, smart pointer is an innovation that relieves you of that responsibility. If you have a smart pointer, then you don't need to explicitly delete the thing that you own. So yeah, and we'll talk more about it as we go. But that's more or less what this unique pointer is. So if you have a unique pointer to this expr AST, then because this class owns this unique pointer, we didn't actually have to write a destructor, the thing that where you do all the cleanup stuff. This cleaning up of this, the object that's pointed to by the pointer is done automatically when an object of this class is not needed anymore. Okay. Alrighty, I'm just gonna copy this one for expedience reasons. And vector, this one uses a vector. It has a string. This call expr AST is like a call expression, which is just something like, fib5 represents like something like fib, whereas the binary expression represents like something like 2 plus 2, right? Fib5 has a callee, that's the name of the function, and an argument list. That's you represent that as an array with a 5 in it. What's a vector? A vector is a dynamic array, so that would correspond to an array in JavaScript, for example. So this guy is going to be a vector of unique pointers to AST nodes, expr AST nodes. Okay. And this stuff, yeah, is the same deal. This standard move is basically saying wherever this unique pointer came from, we're going to move it to be owned by this object. So there's this concept of ownership that's very key to how smart pointers work. And this move operation is sort of transferring the ownership from one part of the code to another part of the code, and in this particular case is transferring the ownership from outside of this class to inside of this class. And we have a couple more AST nodes. I'm just going to copy this. This is a function definition AST node. So I think in this programming language it looks like def, say fib. That's a function definition, and this proto AST is the function signature part of the definition, whereas the function AST contains its own function signature plus the body. And what is in the proto? The proto has the name of the function plus the argument list that would be in here. So there will be an n here, and the n is in the argument list. So yeah, so these two AST nodes represent a function definition. Okay. The next part is going to be actually building the parser. We have set the groundwork for building the parser. We've defined the AST nodes. Actually, there's this red squiggly here, It says it's an incomplete type. Oh, because I need to import vector if I'm going to use it. Or include vector, I should say. Does that solve it? Incomplete. Yeah, that solves it. All I had to do is include vector. Okay, so we have all the AST nodes that we need, at least thus far in this program. The next step is going to be writing the recursive descent parser. I'm going to save this for the next video. So if you're interested in follow along, I'll see you on the other side.